All right, so we're taking a look at line L1, and we're going to go through learning task 1, which is going to be describe system grounding techniques. And I should, before we start into this, caution you that you should have read the preface over here. There's a review section that's only about 3 or 4 pages long that's going to be ahead of this. That's going to talk about your grounding and bonding and some of the stuff that you've covered off in previous years and where we're getting this theory from. Go back over top of that. If you haven't done so already, just pause the video. Once you've done that, jump back into here, because what we need to do is we need to start with that as a grounding, or I guess a basis for what we're going to look at, so that we can actually build from on top of there. Looking into the learning task itself, the features of grounding are really that we're trying to create the system that is going to be the safest. Electrically safe, no shocks, and lower fire risks. And what we're going to go and do is we are going to accomplish this through grounding. There is going to be different grounding on three-phase systems than what there was on our single-phase systems. But ultimately, those 3 bullet points that you see on the first path are on the first page over there are going to still be met. A, we're going to provide a complete path for fault currents that will then be created whenever a system faults. There's no fault current, but as soon as it faults, it will create it, and there will be a complete path. B, we are going to deliver that fault current back to the supply transformer, either through a line or through a neutral. And then C, we're going to allow the associate device, an overcurrent device, so like a breaker or a fuse, or an alarm type, to go and sense that fault and respond. It's not always going to be an overcurrent, and it's not always going to be an alarm type. There's different applications for them. But underneath that, we've got another 2 bullet points that talk about how these systems differ from the single-phase systems that you've looked at before. One of the major differences is we are sometimes going to have tiny values of fault current. Very small, and it's going to be very controlled, instead of a large value of unrestricted current the way that we do on single-phase grounding. And the other difference is that our overcurrent device will not always automatically trip to de-energize the system. In some cases, the system's going to stay energized, and it can be either for a specific amount of time or indefinitely, and there's just going to be a warning that's going to be placed so that qualified users, qualified electricians are going to understand what's going on. Okay, let's talk about the 3 classes of systems we're going to look at. We're going to look at solidly grounded systems, impedance grounded systems, and ungrounded systems. Solidly grounded systems are what we have covered in single-phase studies so far. We've got a system neutral point that is created between voltages, and we directly connect that to ground. And because they're unrestricted type of system, under a fault, there's going to be a massive amount of current that is going to go and flow, right? We know that I is equal to E over top of R. So if we've got a value of voltage over top of a low value of resistance provided by a fault, we're going to go and therefore have a high value of current. That large amount of fault current is automatically going to trip out our breakers, or it's going to go and blow the fuses, or whatever we've got in there for operational safeties. The next system we're going to talk about is going to be impedance, which is where we're going to go and once again have a system with a neutral, but then we're going to go and take that neutral and we're going to connect it to ground, not directly with a conductor, but rather through a very large impedance or opposition to current flow. Sometimes the impedance can be resistive, other times it's going to go and be inductive. But because it is going to have some sort of a choke on the system, whether resistive or inductive, there's going to be a small amount of current that's going to flow, and it's not necessarily going to be enough to trip out our breakers. If we do have these type of systems, we're going to need to have associated alarm devices that are going to monitor and send either a trip signal to the overcurrent or send some sort of a warning so that we understand what is going on. They are a safer system though, and we're going to see them predominantly in the high voltage sections because they do limit the amount of current, which means that we're going to have much less AFIE, or arc flash incident energy. Last of all, we're going to have ungrounded systems. These are going to be delta systems that you have worked with so far this year. There's no electrical neutral point. We know that there's a point that is neutral, but it exists kind of theoretically in the middle of the delta. We have no way to connect to that. So instead, we are just going to go and ground out all of our cans and casings that we are going to go and have. Because of this, we're going to once again monitor our system. If we have a single fault on a delta system, nothing happens. If we have multiple faults on a delta system on different lines, we're going to go and get massive amounts of current that will flow. So those are the 3 main that we're going to look at. We're going to start by taking a look at our solidly grounded system. And the first one we will look at is going to go and be a Y system. According to the code, any systems anywhere from 30 volts all the way up to 750 volts, if they have a neutral, they are required to be solidly grounded. So all of our low voltage systems are going to be solidly grounded. We're also going to be required to go and bond together all of our cans or all of our metallic parts, conduit, etc. that we are going to go and have. And I show a simplified circuit inside of our figure number 1. Figure number 1, we're going to go through it in depth in a minute, but I want to go and point out a couple of things. First of all, I want to go and point out that we have got our actual ground conductor over here going to our ground electrode. So we've got a supply transformer over here. We're only seeing the secondary. The primary could be wire delta. We've gone over those calculations before. It doesn't really matter. We see that we feed from our supply transformer, we feed 4 wires, A, B, C, and neutral, into our service box. In this case, we've got a fusible disconnect over here. From that service box, then we feed out to all the rest of our loads. And we see that we're also taking all of the boxes, and all of the boxes are going to get bonded together. So it's this dotted line that goes around the outside of all the boxes, as well as that dotted line is going to go and get connected back to our neutral at the main ground. This is going to be that bond screw or that ground screw that we're so familiar with. And there's a big reason for this that we're going to cover later on when we look at the current flow. There are 2 different types inside of your code of solidly grounded systems that we need to be aware of. Those are going to be what we refer to as our supply authority and our separately derived systems. CEC rule number 10.2.10 talks about our rules for solidly grounded systems supplied by the supply authority. And if I take a look at this, this would be a Y type of system, 600 volt, 347. Incoming Y, I see that that would go and feed into a service box, and then from the service box, I am sub-distributing out to a bunch of things. So I'm going down to this panel over here. I'm going up to this transformer winding over there, and I'm going over to this automatic transfer switch, which is then feeding down to panel C, where I might have emergency loads being fed out of. What I then see is that I've also got this other definition for what we are going to refer to as being a separately derived system. Solidly grounded separately derived system is going to be any type of voltage system other than what was brought in, so 600, 347, so anything other than that was brought in that is created by the user. And it can be created through a number of things. It could be created through transformers, TX. It could be created through gensets. Over here, this genset is going to put out the same value of voltage, but we are creating it, so it's going to be a solidly grounded, separately derived system, or it could be through other things such as photovoltaics or inverters, wind power, run of the river, anything else that we create that is not coming in from our power authority. We see that all on this side over here, and that's going to be all of these. This is going to go and be a separately derived system, and I see that this separately derived system over to panel A has no connection over to the rest of it, so it's going to need to have its own grounding that's going to be set up because it's a 208/120Y. And I see that this is also going to be, if I've got an automatic transfer switch that has that switched neutral inside of it, this is also going to need to have a separately grounded type of system that we're going to go and create. Okay, let's take a look at what actually happens when we go underneath a fault. Over here, we're looking at that same grounded Y system, and we are going to go and take a look at our fault current that's going to go and happen. The first thing we're going to go and identify is we are going to go and identify the fault. So our fault point happens right over here, where I make connection from one of my lines over to one of my bonded metallic pieces. And this is the most common thing that's going to happen. It's very rare that you drop a live line directly onto earth to like dirt itself, but it's very common that we're going to go and bring it into contact with something that is going to go and be bonded. Ultimately, what we are going to go and see is we're going to go and see current that is going to be delivered by my transformer. I'm just going to trace over top, current coming from my transformer. It is going to go and travel through my service box, through the fuses over here, and then it's going to travel down to here where it hits this point where it can go and make 2 decisions. Does it want to go and take the hard path all the way back through like this, or does it want to go and take the easy path? Well, it's just the same as you and I. It's going to try and take the easy path, which is going to be a low impedance path. See the resistance here? We don't have that type of resistance here on our bonding path. So it's going to go and divert to our bonding path, and then from there is going to go and carry the bulk of the current back along the bond, back up to my neutral. Once it hits the neutral, it is then going to go and return to the transformer. Do you see that red line? It is a complete path over there. It is always, always, always going to go and have a complete path. We never have, where there's current that just hits a fault and just kind of disappears into the earth. Woo, where does it go? It doesn't do that. It's always trying to find its way back to the transformer. Even if we do have a little bit that is going to go and make contact with the earth itself, it is still going to go and use that earth to carry itself back up to the neutral, where it is going to go and rejoin with the rest of the current and go back to the supply transformer. Overall, when I take a look at this, I see that I am going to go and have a massive amount of current that is going to go and flow, because I know that I is equal to my E over top of R. I've got whatever my value of voltage is over here. It could be 122.8, 600, 347, but it's going to be over top of a very low value of resistance. And so therefore, we have a high value of current, and that high value of current flowing through this path is going to go and trip out that breaker. As soon as it trips that breaker, it's going to go and interrupt that current path. This is what we want. We want to create really quickly a current, a large current, that is then going to trip the breaker. It's the whole point of our grounding and bonding systems. We are supposed to go and ground our system at only one point. So only one point in our system is allowed to actually be attached down to ground itself. I'm just going to erase all of these over here. We have got two options for that, though. We can have this that is going to go and happen either at the transformer or at the service box. CEC 10206 requires that ground to go and happen. So if we take a look at where our grounding options themselves are going to go and be, they would be either here, so at my first neutral inside the service box, that's a applicable ground, or if I don't do that one, I've got the option that instead I could go and ground it at my neutral on my transformer, the actual transformer itself. You have to pick one. You are never, ever, ever allowed to go and pick two of these. System can be grounded at either the service box or the transformer, but never both at once. You can refer to CEC 10210A or 10212-1A. That is going to go and give you clarification for those. If I take a look at the path over here, if I ground it at the actual transformer, you'll see that you still have a complete path for current flow that you would go and have going all the way back, because my bond, I should actually just draw that in first, my actual bond itself would have to be attached from here out to this ground as well. That's just the rules of bonding, is that the bond has to be attached at the actual grounded neutral. So what I would see over here is that I would have an attachment that is going to go all the way back to there. So if I follow my path through over here, if I have a fault on the system, it's going to go and travel all the way through. Once it hits here, we can either send some along to the earth, but the bulk of it is going to go along my bonded path back up to the transformer itself. Where once again, we are going to go and complete that path across here. That's going to be for a Y type of system. The other type of solidly grounded system that we could run into is going to go and be that high delta, that grounded 4-wire delta type of system. And the grounded 4-wire delta, we know the rules that we have for this one. First of all, we know that our A late has to be separated out. We cannot keep it inside the same panel. So this is what we're commonly going to see, where we're going to go and have two service boxes. We'll have a 3-phase box and we'll have a single-phase box. And I say commonly seen as if these things are seen all the time. We don't see these systems very often, but if we do, this is common for them to split these two up. What I'll see is I'll see two separate loads, or two separate boxes that are going to go off here. I'm going to have this B phase that is going to get split. Part of it's going to get sent into a single-phase service box. Part of the B phase is going to go to the 3-phase. Same with my C phase. Part of it's going to go to the 3-phase box for 3-phase loads. And the other part of C is going to go into my single-phase box over here, that I'm then going to be able to go and feed the single-phase loads out of. So we got lines over here. We got a neutral over here. We got this neutral point that is going to be the middle of this transformer. Once again, we're going to go and ground that neutral, and then we see that all of my bonded systems are connected together. This box connects to that box, connects to that box, connects all the way back through, etc. This is going to go and give us two pathways for fault current. If we take a look at our single-phase loads over here, I'm going to go and have a single-phase load. If this thing goes and grounds down right over here, so we connect this thing, accidentally connect it to the bond, what we're going to go and see is that we're going to deliver current from our load, travels through the fuses, hits this, where it's got the option to go through resistance or not, and to instead go through this over here, my fault current path, which is going to be back along the bond, and back to the transformer. Complete loop over here, hardly any resistance inside of it, therefore my current is going to go and be ridiculously high, which means that we are going to go and blow that fuse on the affected line. The fuse on the C line is the one that is going to go and blow over here. If we have a single fault on my other set, the three-phase set that I'm going to go and have over here, the A phase, we're going to go and have a fault path that's going to be able to be completed as well. So if I take a look at my A phase, if my A phase itself faults right over here, I'm going to go and have current that's going to deliver from A. It's going to go along here. It's going to go and hit that fault where it goes back to the bonded can, and then it just traces along the bonded can until it gets back to the neutral. Once it gets back to the neutral, it is then going to travel through part of my C winding and across my A winding like that. What we're actually going to go and see, if this was a 240 volts type of delta, which is what it most probably would be, 240 delta over here, because we'd be splitting this and we'd have 120 here and 120 here. We've done that math before. We know that what we have across the very center of that would be a 208 volt fault over there, because that's going to be the vector sum of the voltage across the split C and across the complete AC over there. So we'd end up with a total voltage of 208 volts over top of a very small amount of resistance from our bonding current, which is once again going to go and result in us destroying that fuse that we are going to have over there. Complete path for current flow inside of these. Ungrounded systems operate a little bit different. An ungrounded delta system over here is shown. Once again, we're only looking at the secondary that we have over here. The primary is not shown. It could be Y or it could be delta, as we've gone over before. But we've got a delta type of system. This could be like a 600 volt system, or it could be a 240 or something like that. What we are going to go and have is a ungrounded electrical system, but we're still going to have to go and have a ground that's going to go over to all of my cans. I see that all of my cans are tied together through the bonding pathway back like that. Now, the Delta service, there's a note up top that these things are uncommon. In BC, when it comes to BC Hydro does not like putting these in because we're going to find out they don't automatically develop fault current. BC Hydro likes putting in Y type of systems because they're guaranteed that you're going to go and blow a breaker off of those things. You can still supply three-phase loads from Y or Delta, but the Y is just going to be that much safer. They do have the option, they can connect them if they so choose, but it's not going to go and be an obligation that they have to go and do that. All right, taking a look at what happens underneath a fault. First of all, we should point out that if there's a single fault, absolutely nothing is going to go and happen. We know that the neutral point for a system kind of floats right here in the very, very middle, which means that these ones are all kind of floating roughly above ground over here, circulating around. If we accidentally ground down one of these, so over here I've got a line that's made connection over to the bond itself, there's no complete path for current to go and flow. If I make two connections, as is shown over here, I could split a tiny little bit of current that would be coming in from my main line over here. I could have a small split that's going to go like that and go like that, but ultimately all of that current is going to go and hog back down together where it is now going to go back through that load. So we're not going to go and see any increase in current that's going to go and trip it out. As long as any faults are all on the exact same line, nothing is going to go and happen for actual fault current. We've talked about those little lights before. We'll take a look at those little lights again in the future here. But as far as actual fault current, nothing is going on. If we have two faults, however, all bets are off. So over here we see that we have got two lines that have gotten accidentally grounded or attached to my bond system over here. As soon as this goes and happens, we are going to go and have current that is going to be supplied by one of my lines. In this case, it's my C line over here. My C line is going to supply current, and then my current has the option of going through these loads to get all the way, it can go into here and then split and send some back onto the A and the B. Or alternatively, it's got the option now to travel through the bonded system and make contact with the other grounded down line over here. And as soon as it does that, it is then going to go and make contact with my B line over here. And we see that we are going to go and have overall a complete path for current that is going to go through here. We're going to go and place a full line-to-line value of voltage across that fault, which once again is going to go and result in a ridiculously large value of current. That's going to exist only for a split second. And then it's just going to go, because it's so large, it's going to go and blow either this fuse or that fuse, or sometimes it's going to be able to go and blow both because they both heat up, just way too quickly. We will also have the opportunity for a small amount of current to go and travel around the outside of the transformer, but it is unlikely that we're going to go and have any that's going to travel through the earth itself back to the main ground. If it would travel through the earth, it would just travel from there, join back up with this fault over here, and then be able to make it back out into the transformer itself. So what we're seeing on all these systems so far is that we're always forming a complete loop. A complete loop has to be able to be drawn for us to, prove the circuits themselves. Ungrounded systems are going to be required to be electrically alarmed, as well as they're going to be required to be maintained by qualified person. We're going to take a look at that inside of a separate learning task that's going to be inside of L3, where we actually have to look at the ground fault detection system. So we're going to skip over that, and we'll come back to that one later on. The next thing that we're going to talk about is going to be our impedance grounded systems. And the first one we're going to look at over here is going to be resistance grounding. Impedance is just going to be opposition to electrical current that we are going to go and have. And we can have a couple different ways that we could form impedance. It can be either straight resistance, straight reactance, capacitive reactance, inductive reactance. It could be a combination of any of those that we can go and use. However, the impedances that we will use, the things that we'll use to slow down the flow of current, are usually going to go and be resistance or inductance. We don't want to use a lot of capacitance, because capacitance has this issue where if we've got something that is capacitive and we go into a leading power factor, we can go into a raised system voltage. Our transformer voltages themselves will actually go and increase. This would go and make any sort of a fault that you would have more dangerous. So rather than making a fault more dangerous, we just don't use the capacitive systems by and large. There's a couple small specialized applications where capacitance sometimes can be used, but they're so specialized and rare that we're just going to leave them out entirely in our study of impedance grounding. Systems that we have looked at so far were ones where we had massive amounts of current, but now we're going to go and work on systems that have a neutral that is at a much higher voltage. Remember, any system that's from 30 to 750 volts has to be solidly grounded at the neutral. But now, once we go into higher values of voltage, we sometimes don't want to do that, because that fault, when it would happen, would be so violent that there's a much greater chance of, first of all, massive destruction of components, but also risk to our electricians, plant operators, people in general. So on high voltage systems, we are going to go and use these type of systems, because this resistance, this impedance that we are going to go and have, is really going to go and limit that current down to small values. And as soon as it's a small value, we can get only a tiny little arc. It might be a bright arc, but it is going to be a lot smaller, and it's not going to have the same amount of watts or arc flash incident energy, AFIE. We'll do that through a neutral grounding device, which could be inductive or it could be resistive. Once again, we are also going to go and have monitoring on these systems, but we're not covering the monitoring yet. We're going to first explain the system operation. We'll look at the monitoring later on inside of our L3. Let's start with the resistance grounding. Resistance grounding systems are going to go and have a very, very large resistor over here. Literally, that's all that this thing is going to be. Now, it's not usually going to be a single one. It's going to be multiple ones that are going to be ganged together. But altogether, it's going to go and form a very large value of resistance. Normally speaking, I should have no current that is going to be traveling through this resistance. If I take a look at it, all of my current that I'm going to be delivering out, let's just say that A is high, that would mean that B and C are opposite and halfway in the opposite direction. So my A current would be splitting, coming back in through here, and coming back in through here, and rejoining over there. So we see that there's not going to be anything that's going to be traveling through this ground conductor itself. Well, if I have got 0 amps that are traveling through something, according to Ohm's law, V is equal to I times R, and if this value of current is 0, therefore the value of voltage dropped across is also going to go and be 0. So this is going to be 0 volts when we don't have any fault current going through it. This means that if that's at 0 volts, we've got 0 volts drop between the actual ground and between our neutral. So our neutral is also going to be at that same 0 volt point over here. Okay, let's look at the bonding for this one. The bonding has to be done in a very specialized manner over here. We are going to go and have bonding together of all of our service boxes. We're going to bond that box. We're going to bond our loads together. We're going to bond them all the way back to our resistance device, our neutral grounding device over here. But then we're going to go and see that we are going to go and connect over on the ground side of the resistor. This is so critical that the bond has to be connected on the ground side of the resistor. If you connect it over here, you have just completely defeated the whole way that the system is going to work. We'll cover that in a second. But it has to be connected over here, and then this conductor over here from the neutral grounding device is going to go back up here, and it's going to be an insulated conductor. It needs to be insulated as a white or a gray, and it has to be insulated to the same value as my phase, because we are going to go and drop phase value of resistance across here. So if this thing was a 4160/25, oh, sorry, that's a 2500 volt transformer that we have over here, we would go and be dropping phase value 2500 volts across this resistor here underneath the load. We'll take a look at that as well. Because it's dropping a large value of voltage, even though it's bringing it down to a tiny value of current, there's still going to be a lot of heat, a lot of watts that are going to go and be dissipated by it. So we are going to have to go and deal with cooling off of these systems as well, or we're going to have to go and deal with a relatively quick shutdown. And once again, that's going to go and follow inside of our L3 unit, where we're going to look at how we can go and use what we're sensing off of these to go and do a shutdown. Let's look at these systems underneath a fault over here. Underneath a fault, which we've identified as being this point right over there, we are going to go and have connection over to our bonded path. And so what we will have now is we're going to have current delivered over here by my A phase, once again, traveling through here, traveling through up to here. Now, bulk of my current is still going to go and go through the load back to its transformer like that. But the fault current itself, there's going to be some that's going to go and travel along here. It goes along the bond path, and it's going to go, remember how we have the bond path right over there? Into here, where it has to travel through that resistor and back up to my actual phase over there, the neutral on this thing. If you take a look at this, we know that I is equal to E over top of R. If my resistance is high, which it is going to be because we placed a resistance inside here, therefore my current is going to go and be low. We are going to go and keep it very, very low. Generally speaking, we're going to go and keep this thing to 25 amperes or less. That is going to be across here. 25 amps is a small amount of current to go and to break as well. This is going to go and travel through here, all the way back through. This is going to be our path under fault. Remember how I said it was going to be really dangerous if we would connect our bond path on the wrong side? Let's just go and trace through what would happen if I would go and do so. Let me just erase all of these here. Okay, what I'm going to go and show you over here is going to go and be wrong. We don't want to do this. So instead of us having that there, we have taken our bond and we've connected our bond on this side, on the neutral side of our resistance device. And if we go to a fault in the same spot, we'll put a fault right over there. We're going to go and deliver current from our A phase winding over here through my breakers back down. It's going to hit this fault where it can go across to my bonding pathway, travels along the bonding pathway, and from here is then going to travel, and it bypasses that resistor and heads all the way back to the neutral. This would be bad because we would not have any sort of a drop in the current. We'd have unrestricted current that would go and happen. And if this is on high voltage, we can get a huge amount of AFIE. Has to always be on the ground side of the resistor. Phase voltage is going to be dropped across the resistor as well. If you take a look at this, you can see that I have got just the voltage of the single phase that is going to be impressed across here. And if I take a look, this side is connected to ground, 0 volts. This side is going to be connected to my phase, which would mean that it would have to drop the full value of phase voltage. So I would see this point as rising to phase value of voltage. If we had that 4160, 2500, that would mean that this point here would be at 2500 volts. Which is why we need to go and make sure that this conductor all the way along here is going to go and be insulated. Reactance grounding. Reactance grounding isn't as good as resistance grounding, but it's easier to go and build a reactor than it is to go and build a resistor. We control the currents, but we're not going to get as good of a current. We're usually going to be able to go and knock it down to 50 to maybe 70% of what my unrestricted value of current would be. This is going to be better than a kick in the teeth, but it's not going to be awesome for a lot of situations. We will use this one any place where we've just got kind of a sturdier system. If we've got a system where we really just can't have an arc flash happening, that'll be resistance grounding. But otherwise, we can go with the reactance grounding, which is just going to slow down the rate at which that arc flash would be able to build and the rate at that the current would build, the fault current. So it will still give us some safety inside of here. It does limit as well, just on the, I don't know if you remember going back to some of your earlier years, but second year we took a look at tau. We looked at the rise of voltage across a inductor or a reactor, and those things were sometimes called chokes because they had a slowing down effect. This is still going to go and allow us to develop a large value of fault current, 50 to 70% of our unrestricted, but that 50 to 70% of our unrestricted fault current, we're just going to fault come across here, same as we did before, that 50 to 70% of our unrestricted that's going to go and happen is going to go and get slowed down. And so the overall current is going to go and rise slower, which means we're not going to have it as violent of an explosion, nor as much arc flash instant energy that's going to go and be dissipated immediately. Okay, last one that we're going to go and take a look at is going to be our zigzag grounded. The zigzag transformer is usually more of a filter than it is a transformer. We're not using it to step down to usable voltages. What we're usually doing is we're trying to go and create a system where we can go and allow a delta to go and trip out. You remember how when we took a look at our delta system before, we said we had to go and have two faults before we would be able to go and develop a fault current that would go all the way through that. And we said that if we had only a single line faulted, that single line would not do anything. It wouldn't go and short or trip out anything, no excess amount of current that's going to be created. Instead, it would just go and sometimes split the current to send a bit along the bond, which is legal, but it's not going to be the end of the world compared to some of our other options. So since we have to wait for two faults, that's kind of playing your odds pretty risky over there that you're going to wait for at least two faults. What you can do is you can use the zigzag grounding to go and clear on a single fault. A zigzag transformer is going to be that specialized transformer. We took a look at it before where we are going to go and have opposing windings that are going to go across these things. We are going to go and have B phase that is then going to go across here. We see these arrowheads going into the center, and then my C phase arrowheads going into the center, and like that. And because of the unique way that we wind these things and that we tie them all together, we're going to go and have cancellation of flux that's going to go and happen. It's going to cancel the phase magnetic flux, so the only thing that's going to be left is going to be a tiny amount of magnetizing current, a little bit of bars current, which effectively is going to go and create a high impedance. We could say that this transformer would be seen as if it were a gigantic impedance or a gigantic load through the fact that the Z of the transformer is equal to my E line over top of my I line. Resistance is equal to E over top of I, and if this I over here is a tiny, tiny value of just magnetizing current because we've canceled out all the phase currents, that would mean that this Z would have to be a very large value of impedance. So normally, we're going to go and have it like that. Now, the zigzag winding itself is actually just going to go and get connected across as if it were a load. So we take this transformer, we connect it across, and then what I'm going to do is I'm going to go and bond all of my systems together. Over here, we see that this one's bonded, this one's bonded, this one's bonded, and then I'm going to go and attach them to my ungrounded, or sorry, to my my ground itself, because it's an ungrounded system. It's a delta over here, so we just want to bond all the cans together. But I'm also going to go and make an attachment from my bonded and grounded cans to the neutral of the zigzag transformer itself. This is critical that we have that one on the inside. They're also going to be referred to as being zero sequence filters inside of the Canadian Electrical Code, and if I want, I can even go and increase the safety off of these ones by adding in a resistance inside of this if I really do need to go and have that. How do they operate under faults? Faults is where these things get really, really fun. We've covered how they look when we connect them. Now let's cover how they look on an actual fault. So over here, we are going to go and fault one of our lines. We're going to go and fault this line right up top over here, which is going to go and be my C line. So my C line is going to go and fault over to ground. So I'm going to go and have a large amount of current that is going to go and get delivered from C through my fuses over here, and it is going to go and travel up to here. Now some of it could go back to the loads. There will still be a little bit, but the bulk of it is now going to be able to go and divert. It's looking for the path of least resistance. The bulk of it's going to divert onto the bonding pathway, travel along the bonding pathway, and come back up that, and hit the neutral of my zigzag transformer. If I go and take a look at this line right over here, going across from there to there, I see that this is B line, and I see that this is B line. Is there any potential difference between those two? Absolutely not. So therefore, there's not going to be any sort of current that's going to flow along it. Instead, current wants to get back to the transformer over here, and it's going to want to get back on the A and the B lines over here. So the current is going to enter the zigzag transformer, and then it's going to go and split out of here. Part of it is going to go and travel back along my A line, like that, to here, where it is then going to go and travel back out through my transformer, and part of it's going to go along my B line, like this, over here, where once again, it's going to go and meet and travel back out. So what we are going to go and see is we're going to see a large value of current right over here. On this one over here is going to go and be a high value of current. These ones here are going to be high as well, but they're not going to be as high as what I'm going to go and have on the actual faulted line. The faulted line itself is going to go and trip. It's going to blow that fuse off of that one sooner than it should blow the fuses off of either of these two, because both of those ones, when we take a look at them, we see that they are going to be carrying through smaller values of current. There is a note as well at the very bottom of your page 23 that talks about using a grounded Y winding in place of the zigzag winding. It is impossible to use a grounded Y winding. So I know we get this question pretty much every class, where somebody is going to go and ask if we could just go and use a Y. If I was to take a Y across, an actual true Y over here, just going to line these up with the actual lines. If I were to go and do that, there would be this issue where, for lack of a better term for this, over here, if you take a look at this, this is going to be a line-to-line value of voltage that's going to be delivered back across this line-to-line value of voltage over here. Remember how the zigzag transformer goes and cancels out its flux? This wouldn't do any flux cancellation, so we're going to have a large amount of current that is going to get dropped across from one to the other. And really, this transformer here, this delta, is going to go and try and feed this Y over here, and this Y is going to have next to no impedance across it. There's going to be nothing that's going to go and be seen across it, which means that this is just going to go and dump a ton of current back through. The current's going to go and head back into our transformer. It's going to split some into there, and it's going to go and send some into here. It's going to be the same as having unrestricted values of current, but really it's going to go and double up your value of voltage, because it's going to be going across from the Y to the delta with a direct conduction. So rather than you having like a 600 volt, if it was a 600 volt delta system that you had over here, it would be like you've got a line-to-line short on a 1200 volt one. Very dangerous, can't be done. Anytime that we want to do any sort of filtering, that filtering has to be done through the zigzag transformer itself. But it is pretty freaking cool when you take a look at how these zigzag transformers filter out any sort of a fault current. What we said before, that you could go and place a resistor inside of here, we could place a resistor inside here which would then restrict this value of current that we would have through. So rather than an unrestricted value, we could go to a restricted or a lower voltage value. Neutral grounding resistors and neutral grounding reactors are going to go and look very similar to these drawings over here. For resistance grounding, it's not going to be a single resistor. Instead, it's going to be a bunch of small resistors that are going to be placed together inside of a canister. It's usually going to go and look like a transformer. It's going to go and have a couple of things. We'll note, first of all, we're going to go and have a lot of ventilation, because we're going to dissipate all of that power as watts, right? So we need to be able to go and get this out. Sometimes they're even going to go have powered fans that are going to be in there as well. Secondly, we're going to go and have this thing, which you know as a bushing out of the top here. That bushing is going to be where we're going to go and have our high voltage connection. Remember that during a fault, my actual resistor, which is inside here, is made up of many small ones, that this side of the resistor gets all the way up to phase value, phase voltage that we are going to go and have. Therefore, it's going to need to have a high voltage bushing, because we use these on high voltage systems. And then last of all, we are going to go and have grounding and bonding studs that are going to be usually located on the exterior near the bottom. And the reason for that is because we want to go and connect this thing over to, usually it's going to be a station ground inside of a high voltage station over here. And when we do make that connection, we don't want to place it inside, because there's going to be a lot of heat dissipated inside there. We also want to be able to inspect it without having to pull any covers off. Visual inspection is such a big part of high voltage systems. That's why a lot of stuff is exposed and just barriered off, so you can actually look at it with a pair of binoculars real close to see what's going on. The other one that we're going to have is going to be the grounded reactor over here. Grounded reactor is actually made up of many, many coils of large wire that are just wrapped around. Sometimes you'll actually see the coils, other times they're going to place shielding around them, but usually they're going to be hollow cylindrical structures over here so that we can get maximum amount of airflow that's going to go onto these things. They're going to go and isolate the entire thing from ground, usually because they do a couple of up-down windings of these to keep them spaced. One of these, there's going to be a connection for your ground, and then you're also going to go and have a high voltage bushing. Sometimes the high voltage bushing is going to be proud, where it's going to be sitting up top over here, higher than the unit. Other times it's going to be nestled more into the inside of this, but you will have some sort of a high voltage termination. Last thing to cover off on this learning task is HO, XO points, and jumpers. We have covered off H1, 2, 3, 4, 5, all of these H's and X's inside of transformers before. What we haven't talked about is the zero identifier. And anytime you open up a transformer and you see a zero identifier, that zero identifier is going to be the neutral. HO will be a high voltage neutral if it's a high voltage Y. XO would be a low voltage neutral if it's going to be a low voltage Y. And the manufacturer is usually going to make sure that these things come pre-terminated with a bonding jumper. So there's going to be a bonding jumper inside of the transformer that is going to go over from its, excuse me, over here. From its XO point, they're also going to go and have another bonding jumper that's going to go over to the actual can itself. Remember that we're only ever allowed to go and ground down a system a single time. So it's going to be up to you as a electrician to go and determine whether or not you need to go and remove this grounding jumper over here. Sometimes you'll leave them in. If you've got a Y system where you're going to go and have the actual grounding at the transformer, so I place my ground plate over here at the transformer, connected over to my XO point, then I'm going to go and have my bonding that's going to be connected to the can, and everything else through the rest of the system is all going to go and bond back to that same can over there. That's when it could be allowed. However, if I've got my Y system grounded at the actual service box, then I'm going to have to go and remove that one from it. Let me just go up to a Y type of system here, and we'll just take a quick look at that. If I ground it over here at the box, what I'm going to have to do is I'm going to have to remove that jumper. I'm just going to put a case around my transformer. I didn't have it cased here before, but if I had this thing tied together, the case of that transformer is also going to be bonded all the way back. And if I would have this bonding jumper still going from my XO over here to my can, I'm going to go and have an alternate path for my current to go along. Let's just take a look at that. If we would have a fault on this line over here, we would see that we would send our current out along, we'd hit this, we'd hit our grounding and bonding, and then rather than us sending this thing all the way back up the neutral over here and then back into the transformer, that's the proper way, we could alternatively have some of it that's going to go and travel along here and then travel up here and then hit the neutral. Now ultimately, under a fault, it's still safe because it does still hit that. But we do have two differing resistances over here that of our pathway. We're going to get differing currents that are going to go and split, and we're not going to have just as predictable of a installation. And ultimately, we're really looking for that. We need to go and have predictability on these. So you do have to go and remove one of these two. If you're going to go and ground it over here at the service neutral, you have to remove that one there that comes as part of the transformer. Alternatively, if you're not going to ground at the service neutral, but you want to ground it at the transformer itself, then you would have to go and leave this one in, and you'd have to make sure that all the rest of your bonding is tied together so that we've got a path for my current all the way back through. Just draw that in as being grounded right over here. Okay, you can complete your self-test and on to the next one.